Alright, so we're going to look at proof by contradiction. So we'll start out by looking at the statement if P then Q. So if we assume that if P then Q is false, then we have one of three cases that we have to. Okay, so if we look at where if P then Q is false, that means that P is true and Q is false. That's the only option. So what we're going to do is show that not P is also true. From our assumption that if P then Q is false. So if that's the case, then that means that P and not P, meaning they're both true, and that's not possible. So we know there was something wrong with our original assumption, meaning P true, Q false. So we're kind of wrapped up in logic here, but this is basically almost the same thing as a contrapositive, but a lot of times we're just given existence proofs. So there exists some real number that is a maximum, or there does not exist some real number that's a maximum. So our example will kind of clarify this a little bit, make it a little bit easier to understand. All right, so we have a statement that says there is no smallest positive real number. So we're going to assume that that's not true. We're going to assume to the contrary, that there does exist a smallest positive real number, and we're going to call it x. So we know that 0 is less than x over 2 is less than x, and x over 2 is still a real number. And so we just showed that there is a smaller positive real number than x. And so our assumption was wrong. Our assumption that there is a smallest positive real number is wrong. And so therefore, there is no smallest positive real number. We'll put our tombstone, and we're good. Secondly, no even integer can be written as the sum of an even integer and an odd integer. So again, we're going to assume to the contrary that there is some even integer that can be written as the sum of an even integer and an odd integer. And we'll fix that, the sum of an even integer and odd integer. All right, so we have to call it something. We're going to let that number be n. And we're going to let the even integer and the odd integer be 2a and, well, 2b plus 1, because we don't want them to be consecutive. So by our assumption, n is going to be equal to 2a plus 2b plus 1. And that means that we end up with 2 times an integer plus 1. And remember, we assumed that n was even. And so there's our contradiction. We showed that if we assume that there is some integer that can be written like this, it's going to be equal to 2 times an integer. It's going to be even. And we just showed that it has to be odd. And so our assumption was wrong. This is a classic problem. Square root of 2 is irrational. So we're going to, again, assume to the contrary that the square root of 2 is rational. And then hopefully we get a contradiction somewhere, which means that our assumption was wrong. So if we have a rational number, that means that we can write it as a over b, or p over q, or m over n, where they're just integers. So we'll say the square root of 2 is equal to a over b, where a and b are integers, and we want to make the stipulation here that a over b is in smallest terms. Lowest terms, I should say. Because any rational number, we can always just simplify it repeatedly until it's in lowest terms. Okay, so if we look at that, square root of 2 is equal to a over b. We could rewrite this just by squaring both sides. So that means that 2 well, I should write the square root of 2 squared is equal to 2 is equal to a squared over b squared. So this means that we have 2 times b squared is equal to a squared. And that means that a squared is even. It's 2 times an integer. So remember that we had a theorem. So we'll just write this down just to formalize what we've previously done so we don't forget that that actually had to be proved. If a squared is even, then a is even. and m is equal to qn plus r, where q and r are integers, where r is between 0 and n. Then there's exactly one way to write these, to write m basically. Given m, given n. So for example, if we look at the number, we'll do a simple one, 16. We know that's really 5 times 3 plus 1. So if n was 3 and m was 16, q must be 5, r must be 1. We can do the same thing with negatives if we want. Negative 11 is equal to negative 3 times 5 plus 4, so that means that n would be 5, m would be negative 11, and there q must be negative 3, r must be 4. Notice that r can't be larger than n. And if r is 0 in that theorem, then we would say that n divides m. And remember, we just crossed that out if n does not divide m.